Hello, this is Mr. McGovern, and this is the second video in the momentum series where we're looking at introducing momentum bar charts. Right, I'm going to do a quick comparison first to energy bar charts, which are the bar charts you've already done. And momentum bar charts are very similar, and the reason why they're similar is with energy we were dealing with the conservation of energy, which meant that the energy before in a situation, the total energy afterwards was the same. Here we're looking at something similar, that the total momentum before and the total momentum after are the same. So with energy that looks something like this. We had for example, spring energy, and 5 units of spring energy became 5 units of kinetic energy. The total energy before is 5, the total energy after is 5. So we want to do something similar for momentum. However, momentum has direction. So momentum is a vector. It can be in the positive direction, it could be in the negative direction. And because of that, we have to modify these bar charts. So here's a red car, a little toy car. The mass is 2 kg and the velocity is 1 meter a second in the direction shown. This is what the momentum bar chart looks like for it. So we have it set up here, and you see that down the bottom, where it says before, there's a plus and a minus. Okay, so those indicate direction. So which is our plus and our minus direction? Well, obviously for this car, let's choose our coordinate system to be pointing to the right for the positive. Then we write what we have in our chart. So the object is a car, and you see it's the next thing. It says the M for mass. The mass is 2 kg and the velocity was 1 meter a second. Momentum is mass times velocity, so in this case 2 times 1, 2 momentums, and we put that 2 blocks of momentum on the positive side of the dividing line in the middle there. So we had a toy car that was going the other way, so a yellow toy car, its mass was 1 kg, its velocity was 3. Here's our diagram again. We've got positive and negative. Let's just say we chose, because we had other things going on, the positive still to be going to the right. Then this car is obviously going to the left, so it has negative velocity and negative momentum. So the car is 1, the speed is 3 meters a second, and so we give it 3 momentums, because 3 meters a second times 1 is 3, on the left-hand side of the dividing line, on the negative side. Now with the momentum bar charts, you don't have to put the exact amount of bars that there is momentum. Just like with energy. Say we calculated something and there was 50 momentums, or 61.2 momentums. We don't have to try and draw 61.2 boxes. This is just about getting a symbolic amount of boxes, 3, 4, 5, to show what's going on in a collision. You will do the actual calculations when we use the formula in the next video. So the rules are, for momentum, you need to clearly identify before the collision and after the collision. So this may need you to draw a new diagram, or to draw a diagram that's not there. And I can't stress enough how important this situation is, because just like in energy bar charts, you've got to have there's a before chart and an after chart. So you need a diagram where you need to be able to clearly separate the information into before and after the collision. Add the coordinate system, which way is positive. Fill out your before momentum chart, that's the one on the left. Fill out the after momentum chart, and you use the idea of conservation of momentum to do that. You use the idea that the total momentum before is equal to the total momentum afterwards. And use your bar charts, that's meant to say, to write your momentum equation. So let's go into an example. So here we have a model train set, and the train's being assembled, and an empty carriage, which is coasting along at 3 meters a second, strikes a loaded carriage that's stationary, and the carriage is coupled together. The empty carriage has a mass of 1 kg, and the loaded carriage is 3 kg total. So the first thing was we had to draw the before and afterwards. So before they've collided, only the empty carriage is moving, and it's 1 kg, and the loaded carriage is staying still. After they've collided, they couple together. So they join together. They're moving off at some speed. I don't know what speed that is, but I've decided to call them one big object with a mass of 4 kg, because they're made up of one carriage with 1 kg and one carriage with 3 kg. So when they're together, they're worth 4. Add the coordinate system. It seems everything's going in the same direction, so I'm going to call that direction positive. Right, I've actually got all my information taken out of the question now and into my diagram, so I can probably get rid of the question and just have my diagrams. So now we have to fill in the before momentum chart. So using my before diagram, I'll do one object at a time. So I've got my empty carriage, it's 1 kg moving at 3 meters a second. And I've got my loaded carriage, 3 kgs, but it's not moving. my positives to the right, and it looks like only my empty carriage has momentums, and I'm going to give it 3 momentums. 3 positive momentums as well because it's in the positive direction. Now I do my after momentum chart. So in this case, I could have kept them separate and said the empty and the loaded, but they've joined together, so I find it easier to have them joined together. They're coupled together, their mass is 4 kg, I don't know what their velocity is. But what I do know is that momentum's conserved. The total momentum beforehand, which is 3 momentums, is equal to the total momentum afterwards. Has to be 3 momentums. And that's it. I can use this information now to write an equation. And the equation is that my P empty, P remember is momentum, of my empty one, plus the momentum of my loaded one, which we know is 0, because it's not moving, and that's why it has 0 bars, is equal to my coupled momentum. So that's all I need you to write for now. And in fact, you could have written just P empty equals P coupled, because the P loaded, the momentum loaded, is 0. So you could just get rid of that in the equation. In the next video, we'll use these bar charts and that equation to do some actual calculations.